Okay, last question of the alcohols and phenol tutorial, question 19. Right, so we have 4-bromo-butanone and we synthesize compound E. Okay, so let's take a look at the reaction scheme. Okay, so let's draw out the structure of 4-bromo-butanone, 4 carbon alcohol, 1, 2, 3, 4. Alcohol on carbon number 1. And at 4th position, 1, 2, 3, 4. At the 4th position, we have a Br. Okay, so the first reaction, Al2O3 heat, is a very standard elimination reaction. So we have Br, right, and we eliminate the alcohol. 1, 2, 3, 4. Okay, so elimination of alcohol. Okay, so take note, it's not elimination of your HBr. Okay, then we compare with compound C. Okay, that's the structure of A. So compound C, we have 1, 2, 3, 4, 5. 5 carbons. Alright, so the question is, how can we get 5 carbons from 4 carbons? We therefore need to consider a step up. Okay, so first of all, we have an halogenal alkane. So we can easily convert the Br to a Cn. Alright. Now from there you can take a look. If I just draw the comparison of 5, 4, 3, 2, 1. Alright, and therefore I can convert the Cn to a carboxylic acid. Okay, so you can see the first step basically is to do a nucleophilic sub using ethanolic KCN, heat under reflux. Then B to C is basically acidic hydrolysis. Okay, you use HCl aqueous, heat under reflux. Okay, and let's convert your Cn to COOH. Okay, in step 4, NaHCO3 basically removes the H+. It's your acid-base reaction. You deprotonation of carboxylic acid, and then with I2, then you get this compound. So in step 5, what's the reaction? Step 5, if iodine, basically we're looking at the functional group of the alkene. Alright, so alkene will undergo electrophilic addition with the I2, and then this will lead somehow to the closing of the ring. So let's take a look at the question now, once we have understood the reaction scheme. So just the structure of A and B, alright, earlier we went through already. Okay, so elimination of the alcohol, and then after that, nucleophilic sub of the Cn. Okay, so let's check the answer for A and B. So as I mentioned, okay, elimination of the alcohol, and then after that, replacing the Br with the Cn. Okay, so step 2, ethanolic KCN heat under reflux went through already, and then we do acidic hydrolysis, HCl, H2SO4 heat under reflux. Okay, for the nitrile converting to carboxylic acid. Okay, explain the role of NaHCO3. So NaHCO3 acts as a base to generate the RCOO minus carboxylate salt. Okay, and then in this reaction, we are going to look at how this forms this. Okay, so to understand this mechanism, okay, we need to consider drawing it. Okay, so we have iodine. Okay, so delta plus, delta minus, attack the I. Okay, and then we get a carbocation. Okay, so what happens is that once it attacks, where do we put the I? That we put the I on the carbon with, so we have a iodine over here, we have a carbocation over here. Okay, why do we do that? Because we get a secondary carbocation and that's more stable. And then with the lone pair on the O minus, this can attack the carbocation and close the ring. So if you check the number of carbons, carbon number 1, carbon number 2, carbon number 3, carbon number 4. Okay, and carbon number 5. So in terms of this, let's take a look. Carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay, so you can see the O forms between carbon number 4 and number 1. Okay, so checking, this is basically closing of a ring reaction similar to what we've done for halogenal alkanes tutorial. Okay, so basically what's the purpose? Generates a base. NaHCO3 acts as a base to generate the carboxylate salt. So you have CO minus, which therefore acts as a nucleophile in the ring closure process occurring in step 5. So take a look, this is similar to what I've explained earlier on. So this slow step, you generate your carbocation. Okay, and then your O- will attack the carbon cation to close the ring. Okay, so is there any other possible cyclic ester with the same molecular formula as compound E? So you can see that in this case, we generate the more stable carbon cation, alright, by putting the I on carbon number 5. Alright, but essentially we can have another carbon cation which is less stable though. So let's draw a carbon cation. 1, 2, 3, 4. L1 O, O minus with a lone pair. Instead of putting I at the terminal position, I can put I here with the carbon cation over here. So in this case, I can attack over here, and in this case, I'll form a 1, 2, 3, 4, 5. Alright, in this case, I'll form a 6-membered ring because including the O will be part of the 6-membered ring. Okay, so this is a primary carbon cation, and therefore you get a 6-membered ring. Alright, due to the formation of the second, another primary carbon cation which is less stable. Okay, so you can see over here, instead of adding I at the dominant position, now I have considered primary carbon cation which is less stable, ring closing similar to earlier on, and that's how I get this compound. Okay, now we're supposed to comment on the optical activity of compound E. Let's take a look at E. What's E? E is this compound here. So E is formed via electrophilic addition. So in this case, this carbon cation and carbon number 4 here is sp2 hybridized trigonal planar. This can attack from top and bottom, and therefore you get a racemic mixture. Okay, therefore it's optically inactive. Alright, because it's equal probability of the nucleophile attacking from top and bottom of the plane. Alright, with equal probability. Okay. Now, F is an isomer of E. F only gives 2 monobrominated product when reacted with bromine under UV light, and F does not rotate in fluorescent light. So suggest the structure of F. So first of all, let's analyze this question. 2 monobrominated product when reacted with bromine is your FRS and does not rotate in fluorescent light, which means it's not optically active. Okay, so let's take a look at compound E. Compound E is this. Okay, so C5H7IO2. Okay, C5H7IO2. Because it only gives 2 monobrominated product, this compound must be quite symmetrical. Okay, because it only gives 2 different products and it's not optically active. So first of all, we don't consider any carbon. So one possible structure is this. You can see there's no carbon, and there's an internal plane of symmetry within the molecule itself. Okay, so highly symmetrical molecule, where are the 2 positions I can substitute? Position A here, and position B over here. Okay, so there are 2 monobrominated products. Okay, can? So with that, we are done with question 19.